Well, today I'll be analyzing an LC oscillator. My goal is to demonstrate product computational thinking, uh, thinking model, and show how we can analyze energy transformation in a circuit. So our topic is about LC oscillator analysis. So what's given in this task is we have capacitor and inductor. Also we have initial voltage, which is 5 volts. So let's come to our thinking model. First is pattern recognition. I identify this as a harmonic oscillator. The pattern is about harmonic oscillator. And I recognize a pattern of energy conservation. The energy isn't lost, it just swings back and forth between the electric field and the magnetic field. So the concept is conservation of energy. Where our formula is total energy equals to electric plus magnetic energy. So next step is decomposition. Next, I break the cycle into two states. Like in state A, the capacitor has maximum energy, and current is 0. That's why we have voltage 5 volts and current 0. In state B, the capacitor is empty and the current reaches its maximum. This simplifies our analysis. So voltage is 0 and current equals to its maximum. So next step is abstraction. Now I'm ignoring wire resistance and assuming an ideal circuit where resistance is 0. So this abstraction allows us to use a clean mathematical model of a pure energy swap. So our model is ideal LC circuit, and our assumption is that we have 0 resistance. So next step is algorithm design. My algorithm is actually simple. We just define a capacitor energy, which is half of C capacitor voltage squared. And we'll define inductor energy, which is half of Li squared. So we set them equal and we'll just solve it. So half of Li squared, where I will be equal to, we can cancel halves, and I will be equal to V capacitor over inductor. So the last one is calculation. The easy part, plugging in our values. We have voltage 5, capacitor is equal to 100 or minus 10 minus 9 and 10 minus 3. So the answer is $50 amperes. So this gives us a peak current of approximately 50 milliamperes, actually milliamperes here. Finally, in the data analysis phase, we verify this in Falstead. So let's move to Falstead. Let me reset this. Okay, let's do it faster. And as you can see here, the current is almost the same. The peak current equals to 49.4. That is actually approximately equals to 50 milliamperes. And finally, in the data analysis phase, we verify this in Falstead. As you see on the scope, the measured peak is around 50 milliamperes. The small difference is due to the simulator's internal steps, but it closely confirms our Prada model. So that's it for my B-level task. So let's move to the challenging one. So now for the challenging task, we have an LC circuit with very specific parameters. We need to find the time of the first discharge and the peak current using the Prada model. So our circuit is LC circuit. What do we have? We have inductor 20 milliamperes. We have capacitor 8 picofarads, and our maximum voltage is 25 volts. Yeah, that's it. So let's start with Prada model. So for pattern recognition, I recognize two patterns here. First, the discharge happens at exactly 1/4 of the total period. So and the second, the maximum current occurs at the exact moment the capacitor is fully discharged due to energy conservation. So full discharge time is quarter of period, and maximum current occurs when our voltage of capacitor equals to 0. Let's check it on Falstad. I built it the same circuit but changed the values. So let's watch. Here we can see that capacitor discharging at a quarter of the period, and yeah, so the full discharge time will be equal to quarter of period. And for decomposition, I decompose the problem into two parts. Part A calculates the period of oscillation using the resonance formula, I think we know for part A, the period of resonance formula, Thomson formula, and we'll use this formula to find period. And part B, we'll use energy conservation to find the maximum current Imax, how we did it before in B level task problem. So for abstraction, I use abstraction to treat the discharge not as a complex curve, but as a simple fraction of a cycle. And I also abstract the components as ideal, ignoring any high frequency parasitic losses. So we'll consider it as an ideal oscillator model. And so the next step is we'll put for period here the time formula, and we got the formula for t equals 2 pi square root of LC. And we'll got the formula here, pi over 2 LC. And the last one is algorithm design. My algorithm for part A will just calculate the time. Just use this formula and calculate it. P over 2. For L we'll use 20 millihenries. And for capacitor we'll use 8 picofarads. And if we'll calculate this, we'll got 0.63 milliseconds. And let's calculate maximum current from using that formula that we used in previous task. Voltage C over inductor. We need to just plug in the values. We have 25 volts, 8 picofarads, and 20 millihenries. And now I need to calculate it, and the answer is 0.5 milliamperes. So in the data analysis phase, let's check Falstad first. So our time is 0.63 new seconds. Let's check the discharge time. Our capacitor is discharging, and when it's discharged, the time is it's exactly the same. Like it says 630 nanoseconds. It's exactly the same. It's 0.63 milliseconds, and how you can see the current from the inductor from here at the same time. It's minus, it's because it's discharging, so it's about the direction, so never mind. It says almost 500 milliamperes, and we just proved that our peak current is also 0.5 milliamperes, and we just proved our solution using Falstad model. So that's it for today. Thank you for watching.